So welcome everyone to this last part of our summer school. In the first lecture of this last part, Professor Chab will continue its exposition about structural stability and bifurcation of local dimension in piecewise differential system. Thiago, please.
Thank you, Douglas. Well, we were talking about bifurcations, okay? So the last bifurcation that we saw was this Andronov-Hopf bifurcation for smooth vector fields. And also we saw this version for non-smooth vector field, piecewise smooth vector field at the plane. Okay. Now we start with another classical bifurcation. Not classical, an equivalent to a classical bifurcation. Okay, that is because the classical, I think is the smooth case. But we will say saddle node bifurcation for piecewise smooth vector fields. So let's start with these two vector fields. Okay, what's happening here? We have a vector field y. This is easy to write. This is a transversal vector field to sigma, and this is another one. Is such that for, I will explain this before, but for after, but this for x equals 0, this vector is equal to 0 minus 1. Okay, so we have here a pseudo equilibrium, and for x non-zero, this first coordinate is positive, and the vector field has this phase portrait. Okay, so at this side we have a sliding vector field pointing to the right, and this side too. Okay, so this half plane, okay, the pseudo equilibrium behaves like a saddle, There is an attractive direction and a repulsive direction, okay, at this half plane. And at this half plane, okay, this is the separation of these two half planes. And at this half plane, we have the same direction, the same attracting direction, but at this direction, we also have an attractive behavior. So this is this point behaves like a node for this half plane. Well, let's do some calculations here, okay, in order to prove that this behavior. What we have to do is calculate the first Lie derivative given by this. Okay, so this number is equal to -1. The first Lie derivative for the vector field y, doing the calculation, is equal to 1. So all sigma is a sliding region. All sigma is a sliding region because these two numbers have a or positive signal. And moreover, the first one is negative and the second one is positive. So we can write the sliding vector field following this expression, okay? That Professor Henrique Ponce gave us a beautiful explanation why this is true. Coordinate is 0, okay? So the origin is a pseudo-equilibrium, and it behaves like a saddle node. Okay, now let's perturb the previous vector field, considering a small perturbation here at the y vector field. Okay, the vector field x is the same, and the vector field y, and in the vector field y we put this small parameter here. So look, so observe that the firstly derivative is just the same. It's just the same because here we have this product, okay, and we have this this epsilon times 0. This haven't any role here. So the firstly derivative is just the same. The same happens for x, of course, and the all sigma again is the sliding vector, is a sliding region. The sliding vector field is this in this case. So there is an epsilon, a plus epsilon here at the first coordinate. And so the pseudo-equilibria are given by the roots of this equation. And of course, it has no solution for epsilon positive, okay? And so we haven't equilibria for pseudo-equilibria for epsilon positive, for epsilon equal to 0. We done this before, okay? Is this saddle node case? And for epsilon negative, there are two pseudo-equilibria. One placed here, and then another one placed here. Moreover, the first coordinate of the derivative of this vector field is given by, well, I don't put it here, but it is such that when we calculate this derivative at this point P1, the first coordinate is negative. Okay, so this point behaves like an, here we have this point, and here we have the another point, P1, P2. To be more precise, there is a 0 here, but I will omit this, okay? So we have the point P1, which behaves like an attractor for the sliding vector field, and the point P2 has a derivative of the first coordinate of this vector field, negative, positive, and so it is a repulsive. It has a repulsive dynamics at this unidimensional vector field. So when we see the bifurcation diagram, what we observe is that for epsilon positive, for epsilon positive, there is no pseudo-equilibrium. For epsilon equal to 0, we have a saddle node, okay? And for epsilon negative, we have these 2 points, okay? The first one has an attractive dynamics, and the second one has a behavior like a saddle. Okay, so there is an analogous to the saddle node bifurcation for piecewise smooth vector fields. Moreover, this equilibrium is a codimension. The vector field present in this equilibrium is a local codimension 1 vector field. Is locally codimension 1 vector field. Okay, and we can put all the codimension 1 vector fields in a set. Okay, that will be this set omega 1 here, composed by all these subsets, where each one of these subsets are given at this list. Okay, here we have here we have all codimension 1 planar important piecewise smooth vector fields. They are the following. The set omega f is the set of piecewise smooth vector field, such that the origin is a hyperbolic focus of x, and the vector field y is transversal to sigma. Moreover, we get here a generic hypothesis about the sliding vector field. Okay, this is necessary. So what's happening here? So here we have a boundary equilibrium. There is a focus of the x vector field, and the vector field y is transversal. Okay. Of course, at one side of this focus, there is a sliding vector field. This region can be a sliding region or an escaping region, depending on the orientation of the vector fields here. Okay, but always there is a crossing region and a sliding or escaping region at each one of the sides of this point. Well, the second set is omega n, that corresponds to the vector fields presenting such that the x vector field has a node, a hyperbolic node, a hyperbolic focus. Okay, because we are talking about codimension 1 vector fields, so these singularities must be hyperbolic. The picture is the same, but the x vector field has a node. The third one is the set of smooth vector fields presenting such that x has a hyperbolic saddle. The picture is the same, the behavior is the same, just changing the hyperbolic equilibrium of x by a saddle. Okay. This one is a typical singularity of a smooth vector field, such that the x vector field has an isolated cusp, and the y vector field is transversal. So the y vector field is transversal, And now the x vector field, this is not an equilibrium. The x vector field, I will draw like a segment. This x vector field has a contact of order 3 here, okay? There's a contact of order 3 here. And in a neighborhood of this point, the x vector field is transversal. And the x vector field has a tangent point just at this isolated cusp point. Remember that if the x vector field has a quadratic contact and the y vector field is transversal, this is a codimension 1 vector field, okay? This is structurally stable. Now we at this set omega c, we are taking a tangents of a higher order. I don't know what's happening here. Okay, the set omega p, the set omega p is the set where x has a visible fold point at the origin and y has an invisible fold point. It's like a thing like this. Okay, at the same point, the x vector field has a visible fold point, and the y vector field has a invisible fold point. This p is because I call this case the parabolic fold, a parabolic case, okay? Because the picture looks like a parabola, okay? Again, we have to distinguish some case here, because we can look for the orientation of the vector field y. If the vector field y have the same orientation of the vector field x, so here at the left and on the right we have a crossing region. We have crossing regions. But if the orientation of the two smooth vector fields are in a positive sense, so at both sides we haven't crossing regions, and we have to look what's happening here. But here offshore we have a sliding vector field, and at this side too also we have a sliding vector field. The orientation, I will not put the orientation of the sliding vector fields here because it must be studied. But there is an hypothesis here that this sliding vector field, even in this case, is not zero. Okay, it's possible to obtain piecewise smooth vector fields such that this point is not an equilibrium of the sliding vector field when we extend this sliding vector field to the boundary. Observe that this value is zero when we are in a two-fold singularity. So we are considering there the extended vector field, okay? Because this one is not well defined, but we are considering the extended vector field. Okay, and okay, the next set is this one. There is an H here because the phase portrait looks like an hyperbola. Okay, something like this. At one side we have a visible fold point, at the other side also is a visible fold point. This case is omega E because uh, because the phase portrait looks like have an elliptical behavior, but we have to consider this genetic hypothesis that provide us that the first return map is not equal to one. So the first return map does something like this. And it's not a center, okay? And the last set is the set of, because this is a higher codimension. The last set is the set where it appears just a cell node, okay, just like we saw before at the previous example, okay. So considering all these subsets together, we have the following. This set omega 1 contains all two-dimensional codimension 1 piecewise move vector field. Okay. When I talk codimension 1, I already talking that this is structurally stable when restricted to the set omega r less the set of structurally stable vector fields. Okay, following the Sotomayor definition of codimensions. Okay, so these are the codimension 1 vector fields at the plane. This list and the proof of this result is showed at this paper, and also, but not the complete list, okay, at these two papers. In fact, these two papers, everyone who wants to study bifurcations of piecewise move vector fields in any dimension have to read this paper, okay? They are very classical, and the ideas here are necessary to understand the bifurcations of piecewise move vector fields. Okay. So let's do an improvement here. Until now, we saw bifurcations of bidimensional, of planar, in fact, vector piecewise move vector fields. We saw this saddle node, and also we saw the Hopf bifurcation. Okay, the Hopf bifurcation. This Hopf bifurcation is the case omega E at the previous list. Okay, we have a phase portrait like presenting an elliptic behavior. Now I will present to you a three-dimensional bifurcation. in piecewise move vector fields. In fact, to the best of my knowledge, a list of such singularities is not exhibited. Okay, just like there exists a list of codimension one vector fields at the plane. To the best of my knowledge, there isn't a list, a full list, a complete list of codimension one three-dimensional piecewise move vector fields. And this is an exercise to you, okay? Also, you can do the following exercise. Produce a list of codimension two piecewise move vector fields at the plane, okay? At this paper here, there are some cases, okay, and there are another some cases at the literature, but there isn't, to the best of my knowledge, okay, a list of codimension two piecewise move vector fields at the plane. So this is an exercise for you too. For you, you can 3 days to do. Okay. So let's consider this the vector field, the codimension one vector field given at this paper. What's happening here? Well, we have a three-dimensional vector field, okay, and some hypothesis here. This number, these values c minus and c plus are constant, but there is this relation between them, and there is a variable here, a variable parameter that is me. Okay, that's me. So let's do some calculations, the same calculations of every that we done every time. We have to calculate the first Lie derivatives, okay, that are these expressions. And using these expressions, we saw that there are two tangent lines, okay, one corresponding to this one and one corresponding to this one, which are these two tangent lines at the plane x equal to 0, okay, x equal to 0 is the switching manifold. So here we have the switching manifold, x equal to 0, and at this manifold there are two fold curves. Moreover, these two fold curves, if me is equal to 0, okay, these two fold curves are parabola that meet each other quadratically. Okay, so there is a fold curve here, next fold curve, okay, no, and a y fold curve, and the intersection of these fold curves is not transversal. Moreover, the second Lie derivatives are given by these expressions, and there are places where both of them are or both of them, for example, the second one is positive, the f minus 1 is positive and the f plus 1 is negative. So which we have here is this curve, this y-fold curve here corresponds to invisible fold points, and also the x-fold, the x no, because I'm using another uh, notation here. Here I'm using f plus and that f minus, but the above vector field also has an invisible fold point. Okay, this is clear, and we will consider the we will state the problem just at the region where we have this case. Okay, of course there are some values of x such that this expression is 0, and after this expression is negative. For example, this one, this point where this expression is 0 is a cusp point. Okay, we 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 could study this, but we will not do this today. We will consider just the region where we have uh, invisible fold points for both vector fields. Okay. As we can see, you can see these tangent sets, not lines, but tangent sets intersect transversely at 2. Okay, there is uh, this is not true for all me, but for me positive, this is true. Okay, this generically these tangent sets meet each other in 2 points. Okay, just like here, when me is positive, or when me is equal to 0, they have this non-generic intersection. And when me is negative, these parabolas have no contact, okay? Because the expressions, their expressions are this one, okay? Okay, this is the first thing that we have to observe here. So let's go. Okay. When we have this intersection, this transversal intersection, when we have me positive, the intersection of these two curves happens, intersections happen in Teixeira singularities, okay? Because all tangent points here at these curves are invisible for both vector fields. So the intersections happen in Teixeira singularities. These 2 points are Teixeira singularities. This is interesting. And this when me is between 0 and c, where c is given by this number is the number where we have this is related to these inequalities. Okay, this is related to the domain of the where we have just invisible singularities of both vector fields. So for me, smaller than C, where C is this, we have that both both fold singularities are Teixeira singularities. Okay, and there is a degenerated T singularity at the origin, for me equal to 0, that corresponds to this case. Okay, so these two Teixeira singularities crash at this point, and so they disappear. In order, and this behavior is obtained by the variation of just one parameter, okay, of by means of the variation of the parameter me. These curves picture here, I will explain at the next slides, okay? This phase portrait here, for example, I will explain at the next slides. So let's go. What do we have to do? We have to study the sliding dynamics and the crossing or returning dynamics around these vector fields, okay? Around this singularity. So let's do this. The first thing is to study sliding dynamics. In order to study sliding dynamics, we have to compute the sliding vector field, okay, which is this one. Doing the same calculation, the expression is the same as before. So, okay. So, if me is positive, okay, this expression, this expression here, this denominator is given by this, which is positive. It is positive. So, since this value is positive, we will, in order to study this vector field, we will study just this part of this vector field, okay? We will study just this part of the vector field, which is topological equivalent to the sliding vector field when this value, it's not a value, it's variable, but when this expression is positive, okay? When this expression is positive, the singularized sliding vector field, which corresponds to this vector field, is topologically equivalent to this one. Moreover, okay, moreover, I will talk about the moreover here. and so the singularized sliding vector field is this, okay? The two-dimensional, because at the third variable we have a 0, so we will study the two-dimensional sliding vector field that is placed at the plane z equal to 0, which is sigma. Now, an important remark here. At the escaping region, at the escaping region, and let's look here. At the escaping region, okay, which is, here we have a sliding region and in every, just like I told you at the last talk, in every the singularity, okay, we have uh, the region sigma is separated into four regions, where, for example, we have a crossing region, a sliding region, and a escaping region. Okay, so since we have here a T singularity, we have a configuration like this, and here we have a crossing region. Here we have a crossing region, and at this side we have an escaping region, and at this side we have a sliding region. Okay, so at the sliding region, the singularized sliding vector field have the same topological behavior of the sliding vector field, but at the escaping region, this number is negative. Okay, this number is negative at the escaping region. So at the escaping region, the singularized sliding vector field have the same topological type behavior of the sliding vector field, but reversing the time. Okay, this is an important remark here. Okay, so proposition, it's possible to prove that it occurs a saddle node bifurcation at the origin of this singularized slide vector field. Okay, when we vary the parameter mi. Okay, moreover, for me, positive, let me see. Okay, for me positive, there are two equilibria, as being one of them node and the other of them a saddle. Okay, so I don't know. So what's happening here is for me positive, we have at the sliding region that this point behaves like let me see, behaves like I don't wrote this. Okay, behaves like there is a like this. So this point behaves like a saddle, okay, and this point behaves like a repulsive node. Okay, and for me equal to 0, these 2 points crash, they collapse at a single point. Okay, just like a saddle node point. And for me negative, this equilibrium does not exist anymore. Okay, this is picture here. This is the picture that appear here. Okay, this is these points are the saddle and the node. This is the saddle node point. Okay, and in here we haven't any equilibria. Note that this region is the escaping region. So the singularized sliding vector field must have its orientation changed, okay, according to this remark, okay, because this number is, which corresponds to this one, is negative, the difference of the two Lie derivatives, okay, because this number is negative. So with this, we we can understand the sliding dynamics. The sliding dynamics have this bifurcation, okay, and also the crossing or returning dynamics also will present bifurcation. Well, what's happening here is the following. The first return map has not a saddle node, but a saddle center bifurcation at the origin, okay? So what's happening here is that for me positive, there are two equilibria of the first return map, okay? So this plane is the sigma, and for example, there are two equilibria of the first return map that are the test singularities, okay? The test singularities are fixed points of the first return map, okay? And for the other points, for example, if we are here, the x vector field plays this point here, and again the y vector field plays this point here, okay? Not here, sorry. Following this, the y vector field plays this point here, okay? At this same curve, but at the left, because there is an orientation here. Okay, we have a behavior like this, and this first return map returns to this curve, okay, following this orientation, because this point is a center, behaves like a center for the first return map, okay? And this point behaves like a saddle for the first return map, okay? These points pictured here are the points where the first return map is rating the Sweet manifold sigma, okay? So there is a saddle center bifurcation at this situation. Of course, this is the case me positive, and also we also have the case me equals to zero, that is something like, so here we have the escaping regions, okay? When these parabolas, look at the parabolas again, okay? When these parabolas have a non-generic contact, and the first return map is doing something like this, okay? There is an equilibrium here also, but a non-hyperbolic equilibrium of the first return map. And at the case me negative, okay, all this region is the escaping region, and the first return map haven't equilibrium. Okay, so also occurs a bifurcation for the first return map at the same bifurcation parameter, okay? At the parameter me equals to 0. So it's okay for the first part of this last talk. We have here a codimension 1 by three-dimensional bifurcation. Douglas?
Okay, Thiago, thank you. I have a question. Could you go back to the figure again?
Which one of them?
Last one,
This?
this one. Yes.
This?
Yes. So in this, around the fixed point with a center dynamics behaving like a center for the Poincaré half map, what's the future of this iteration? I see that it's going to the boundary of the sliding dynamics, right? But it's converging to a limit cycle. These boundaries are constituted by
No. Looks, the future will be here, okay?
this is a
And
fixed
then,
point.
no, because when the trajectory meets this point, okay,
Uh-huh.
or even a point inside this region, okay, not necessarily the trajectory will crash sigma at this boundary point. The trajectory can return to sigma at a point inside this region. Okay.
Okay.
And then what's happening after this is that the trajectory will follow the sliding dynamics.
Okay. So the returning dynamics just stop.
Yes. Once the trajectory meets this region, even at the boundary, okay, this will slides until here.
Okay. Okay, thank you. Any question, comments? So if not, we will have a break now and we should come back in 10 minutes.
Ah. Just a last comment. These three-dimensional vector fields can be used to model uh, electronic power system. Okay, this is related to real world situations. Okay, this three-dimensional vector field corresponds to some power electronic model. In fact, this author, Rony Cristiano, and also Professor Daniel Pagano, they are experts in power electronics. This is okay. No.
Pagano is an engineer.
Yes, they are engineer. Electronic, they are electric engineer.
Okay.
I don't know if electric is the right word, but they work with this electric power systems.
Okay, can we stop now?
Yeah.
Okay, so let's have a break and we return in 10 minutes. Thank you. So, please, Jeff.
Thank you. So, in order to finish this course in this talk, I will talk about two applications of piecewise move vector fields. Not at all an application, but there are two problems here, two real problems. One of them is about the source code, and the other one is about the about an HIV dynamics. And these two problems can be modeled using piecewise smooth vector fields, and we will obtain uh, topological properties of these models using our theory. Okay, so the first one is a SARS-CoV model. This model was presented at this paper of the science. Okay, and the authors just present the model, but they don't study the model. The model is this. Okay. So what's happening here? What are these letters? Okay. The letter E is corresponds to the infected individuals. The letter S corresponds to the susceptible individuals. Okay, individuals that can have a infection. And R corresponds to the removed individuals, those ones that die, and those ones that are cured, or well, at this time, 2020, okay, uh, people still believe or believing that cured person cannot have an infection again. Okay, and the sum of these two populations is equal to the full population, is equal to 1. Okay. Well, so we will study the variation, the variation of these these variables. Okay. The parameters alpha and beta corresponds to the transmission rates, to the transmission and the recovering rates. Okay. Moreover, the containment of the population is done by a tax kappa 0. This means, for example, if a government says that that people must to be at home, okay, all the population must be at home, or even if the government say that some some individuals, some workers, okay, must be at home, and another ones can go at your work. This is the kappa zero rule, and the parameter kappa corresponds to that person, to an individual that is contaminated. Okay, so this individual must to be isolated. All these individuals, okay, all contaminated individual must to be isolated, and not just isolated or not, like if it work is essential or not. Okay. The variable x does not affect the three first ones, okay? And it corresponds, let's look here. There isn't x here and here and here, okay? And it corresponds to the symptomatic individuals which are in quarantine, okay? But this variable does not affect the other ones. Moreover, the variable r also does not affect the variables s and y and I, okay? There isn't r here and there isn't r here, okay? So we can solve a two-dimensional system and not a four-dimensional system. So we will study just this two-dimensional system, okay? And this is a planar system. This is a planar system. At this planar system, since we are interested in piecewise smooth vector field, we will consider two situations. When there isn't restrictions concerning the circulation of the population okay, and the second case where these numbers are not zero and there is restrictions about the circulation. There are restrictions about the circulation. Okay, but when we will impose or not these restrictions? Well, the restrictions will be imposed when the infected number of individuals is equal to a value IM, okay? IM. When the number of infected individuals is smaller than this number, we will not apply restrictions. And when the infected individuals is greater than this number, we will apply restrictions. Okay. A natural question here is the following. If the health system tolerates this number of infected individuals, okay, the health system has a number of places, okay, and this is the number of places that are available at the health system. So if this is the number tolerated, what is the number I am, okay, and what is the number kappa 0 that we have to have in order to not collapsate, in order to not to have a collapse, okay, of the health system. This is our main objective here, is to provide these numbers, okay? This means when we have to impose restrictions, and what must be the, the kind of restrictions in order to do not collapsate the health system. So let's do this. In order to do this, there are two numbers here, very useful, used, and that each one of us already listened this these days, okay, that are the basic numbers of reproduction. So there is a basic number of reproduction of the virus. If we haven't restrictions, we have restrictions, and another basic reproduction number if restrictions are imposed. Okay. Of course, this number is bigger than this one. Okay. And look, there are some way to measure these numbers. Okay. For example, the basic number of the basic reproduction number when we haven't a restriction is the quotient between these two taxes. Okay. Remember that alpha and beta correspond to the transmission and the recovering taxes. Okay, so when the reproduction number without restrictions is smaller than 1, this is a general fact, okay? The disease extinguishes naturally, okay, naturally, without any other occupation, okay, occupation. But the disease extinguishes naturally. And so we will study the case where this number is bigger than 1. The next picture illustrates the dynamic behavior according to the values of these reproduction numbers. So let's look here what's happening with the two-dimensional model, okay? The first thing is that the population, the population is smaller than 1, okay? 1 is a number here, but of course there isn't just one individual here, but it's a normalization of the population, okay? The normalization of the population. And moreover, this is the line which corresponds to the s plus 1 equals to 1, okay? Here we have the variable I, and here we have the variable s, okay? So this is the number I capital M corresponding to the health system, to the health system capacity, okay? And this is the number of infected individuals that we will consider in order to apply or not the restrictions. And let's see what's happening here, okay? First, if the reproduction number without restrictions is equal or bigger than this value, okay, which corresponds to this one, okay? to this value, we have this behavior. This means that if you consider a initial condition here, so the trajectory by this point will converge, will converge, okay, to the situation where y I is equal to 0, okay? So in this case, when I is equal to 0, there isn't infected individuals, okay? The same occurs for all other initial condition, okay? If you have this number of infected individuals, and we will start our protocol, okay, at this situation. So we can see that after some time, okay, we will have 0 infected individuals. So this protocol is good for this scenario, okay? Now let's see the next one. The next one is when this number becomes smaller, okay? Becomes smaller, and this number is always smaller than this one. But let's look now when this number is equal to this value, okay? Is entering the region of interest, okay? So this number is equal to this one. What's happening here? What's happening here is that in this case, we have a sliding region here, okay? We have a sliding region, but look at any initial condition for any number of infected individuals, the trajectory by this point will reach the line I equal to 0. In particular, if we have a point here, for example, or here, the trajectory will reach the sliding region, and so it will follow the sliding vector field until this point, this tangent point, and so it corresponds to a fold regular point, okay, just like we saw it at the theory, and so it will reach the line, the x-axis at this point, and there isn't infected individuals in this case. Again, let's see another case. This number is still smaller, and this one too is smaller, okay, than the previous one. So what we have here? We have here a sliding region, and here we have a crossing region at this segment, okay. But if we are in a point here, the trajectory will have this behavior, and so again, after some time, we will have 0 infected individuals. Moreover, this is a tangent point here. There is a tangent point here, okay? There is a tangent point here for this specific value of this number. There is a tangent point here. And any trajectory is reaching this line, okay? Except by this point, okay? But any trajectory is reaching this line. Another case, if this number is smaller and this two, this also is smaller, the situation is this. But look, at this situation, we have a region here, corresponding to points, to the initial conditions, to number of I and S, okay? Such that if you take the initial condition here, if you apply the protocol, the intermittent protocol of control here, the health system will be in collapse, okay? You have a collapse here. There will be places at the hospital for all infected people. Okay, this is a matter. This is a real problem. And if we continue this problematic region grows, okay, grows up, and there is even a situation like this where even if we take an initial condition here, okay, even if we take an initial condition here, with a number of infected individuals close to zero, okay, close to zero, we still will have that the health system does not have capacity to all infected individuals after some time. Okay, so we need to take care about this dynamic in order to control these numbers. Okay, and that the paper which we have submitted, we explicitly show these numbers. This number, not this one, but we found this number, okay, such that for any initial condition, the health system is not in danger. Okay. Okay, this was the a compilation, okay, of this system. The calculations here are very simple, but the results are, in my opinion, interesting. And now the last model is a model for the HIV virus. Okay. Well, there is a biological introduction here. Actually, the treatment of this disease is based on two medicines. Okay, one of them. Let me see what. Let me go here. Okay, one of them has an effectiveness for something, some specific, some biological thing. I will not explain this. And another one has effective for another biological thing. They must be combined, okay? But there are these two drugs, and so the number of the dynamics of these infected cells are provided by this, are given by these models, okay? What's happening here, okay? What's happening here? Let me explain which are these parameters. It means these parameters, okay? First of all, the nowadays treatment of this disease permits, okay, allow us to have some periods without any treatment, okay? The drugs are good enough in order to permit, to allow some periods without treatment. This is good in order to provide a better life to people, okay? And when we will impose or not the treatment, when the the good cells in our body reach some specific value. When this value is smaller than this CT, okay, we apply the treatment, the therapy, and when this value is bigger than this critical value, we stop the treatment. Okay. Based on these works here, okay, there are, I put 3 of them here, but there are another ones. Look at the journals where they are placed. Okay, there are first principally these 2. There are very good journals, and based on uh, these papers that study the interruptions of the treatment, okay, we establish these 2 move vector fields that will be combined in order to produce a piecewise move vector field. Okay, so the letter T, okay, and the letter T corresponds to cells. I wrote this. It's here. The letter T corresponds to uninfected CG4 plus T cells. Okay, this is the number, the name of the cell. It's a defensive cell of our body. Okay, so T is the number of these uninfected cells. T star corresponds to the infected cells. Okay. Okay, to these T infected cells. V corresponds to the concentration of virus, okay, of the concentration of virus, because it's possible that a T cell is infected, but this cell does not does not have a sufficient virus inside. Okay, and this infected cell does not plays an important role here at the concentration of virus. Okay, when the cell has so much virus that it uh, has an influence here, we put the cell here and not here. Okay, so this is the means of these variables, and the the these T cells, they have not a uh, natural, our body produces not naturally these cells, okay, and naturally these cells are dying, okay, naturally. But some of these cells, when are in contact with a V cell, this is infected, and this become here, this comes to here, okay? So the cell become infected. And the infected cells, the variation of the infected cells have this factor, and also a factor negative, which corresponds to these infected cells that naturally dies, okay, and these infector cells that become a worst cell, a V cell, okay, which also naturally can die. Okay, this is the meaning of these equations. And now, if you impose the treatment, this drug with the drug would have this tax of effectiveness, okay, will control this iteration between uh, a good cell and a bad cell, okay, and this drug will help our body in order to produce a small number of infected cells, okay, and the another drug will be helpful in order to in order to produce a smaller number of really bad cells. Since the cell is infected, since the first drug fails, okay, and the cell is infected, there's another drug will be useful in order to produce a small number of really bad cells, since the cell already is infected. Okay, so this is the piecewise smooth system. Okay, and when this number is bigger than this critical value, we will not apply the treatment, the therapy. And when this number is smaller than this critical value, okay, because an infected cell also can help our body, okay, even if the cell is infected, it also can help our body. So there are some canonical standard values of these parameters, okay. They were these numbers were founded in experimental experiment, okay. And again, and always, there are the basic numbers of reproduction, okay. without and with the treatment. Okay, I will not uh, explain why this value. Okay, but look at the RC number. The RC number is equal to this one without treatment multiplied by the effectiveness of the drugs. Okay. So of course, this number is smaller than this one. Okay. Again, at the model, we can at the 3D model, we have tangential sets. Okay, tangential sets. The written with these letters, and moreover, here we have a distinct situation, because I will return here, but let me go to the picture. In this case, the tangential set of both systems are the same line. Okay, both systems, the X and the Y system, both of them have the same tangential line. Okay, the same tangential line. And at this tangential line, we define a tangential sliding vector field. Not a sliding vector field, because sliding vector fields are defined for sliding and escaping regions. But here we have a tangential sliding vector field. Why we are defining this? Because, for example, if you have a vector field here, tangent to this red line, and another vector field, also, it's possible that these vector fields, the vector fields at these points provides a vertex here. Okay, and so we can define at this case a tangential vector field here using a linear combination of the vector field corresponding to this tangency and the vector field corresponding to this another tangency. Okay. Again, to the best of my knowledge, this is not provided. This is not done at the Filipov book. Okay, Filipov doesn't consider this case, but it's possible to have a sliding motion at this simultaneous tangents points, this simultaneous tangency curve, tangency line. Okay, and this is defined here with this tangential sliding vector field given by this expression that I will not explain, but the meaning is the same of this picture that I told at this picture. Okay, so let's go to the model. The switch manifold is given by the switch manifold sigma is given by the image of the zero by a smooth function f given by this. Okay, so it corresponds to a plane at in R3. Okay. Moreover, um, over this plane, we will consider this vector field, and in the other case, we will consider this vector field. An important thing is that these vector fields that I gave before, these vector fields are this one, okay? These vector fields have equilibria. The x vector field has two equilibria, and the y vector field has two equilibria. And the sum, moreover, one equilibria of x coincides with one equilibria of y. Okay, they share same equilibrium. Of course, for one vector field, this equilibria is virtual, and for the another vector field, this equilibria is real. Okay. The sum of the two first coordinates, the coordinate t and the coordinate t star of this equilibria are given here. Okay, I will not give the details here, but this is the sum of the two first coordinates of the equilibria of the smooth systems. And so let me go here to the picture. What's happening? There are also two cusp points for the vector fields. A cusp point for the x vector field, pictured here. Okay, so the x vector field has a visible tangent until this point, and after this point, the vector field has an invisible fold. Okay, and again, for the y vector field, there is a cusp point here, and that for these points, the y vector field has an invisible tangent set, and for the other side, the y vector field has a visible fold points. Okay. Moreover, when alpha is smaller than delta, and of course, R0 is positive. Okay, again, if R0 is positive, no, is bigger than 1. Again, if R0 is smaller than 1, the system, there is no way to apply a treatment because the virus will vanish, okay, naturally. So it's natural to consider this case, okay. And if you have these inequalities concerning the sum of the two first coordinates of the equilibrium, okay, that I told before, then there exists a region, a sigma region, such that which is a globally asymptotically stable set for the piecewise smooth vector field. In fact, this is the region, this here we are at sigma now, okay? This region plus this region, okay, corresponds to a region of to the base of attraction of the piecewise smooth system. Okay. Sorry, guys. We have a new a new student here. And he's coming for the window. Let's go. Let's continue here. Our last theorem. Our last theorem. Uh, our last theorem talks about a bifurcation at this model. About a bifurcation at this model. Okay, keeping the same hypothesis as before. There exists a parameter me, okay, such that if this parameter me is negative, now it's important to observe that we are looking for the returning or crossing. In fact, this is a crossing for the crossing dynamics. Okay, so there is a parameter me such that the crossing at the crossing dynamics, we can ensure that this equilibrium P, which is an equilibrium of the tangential sliding motion. Let's do a zoom here, okay? So we have these two cusp points, okay? And inside this this tangent line, we define the tangential sliding vector field, and here we have a fixed point of this tangential sliding vector field. This is the point P, okay? And in a neighborhood of P, we have a return map well defined, okay? Because this point corresponds to the, because between these cusp points, we have invisible fold points for both vector fields. So we can define here a first return map. And we will look for this first return map at this last theorem. Okay. So here we have an attractive direction given by the tangential sliding vector field, and at sigma, okay, this is sigma, this plane is sigma. We have the first return map. We have that the first return map has these dynamics, okay, when me is negative. This means that the point P is an attractor, okay? Moreover, if me is positive, the first return map is repulsive. And the first return map is repulsive, but again, the sliding motion, the tangential sliding motion, has an attractive behavior, okay? So for me, positive point P behaves like a saddle, okay? For this crossing dynamics. And moreover, of course, for me equals to zero, it's a weak attractor. And when me is positive, okay, since a kind far of this line, the crossing dynamics is converging to the tangent line, the same happens here. But the point P has the line P, all the line has a repulsive behavior. So it's possible to prove that there is two fixed points of the two attractive fixed points of the sliding of the crossing dynamics. In fact, these points corresponds to a limit cycle at the three-dimensional dynamics. Here, it's pictured this limit cycle, and here we draw some nice pictures using those numbers of the parameters obtained in a laboratory, okay, and varying this parameter me, we have these situations, or even making a zoom here, okay. The first case where lambda is negative, we have here the two cusp points. This is the equilibrium of the tangential sliding vector field that becomes essentially at the same topological type if me is 0, and after if me is positive, there is a crossing limit cycle here around this situation. In fact, in all these cases, we saw that the protocol, the treatment, the therapy the therapy will not eliminate the virus, okay? The treatment will not eliminate the virus. The number V is not 0, but it is placed in a region where it can be controlled, okay? And the disease is controlled. Okay. Thank you very much for your attention. It was a pleasure to me to give this talk.
Okay, Thiago, thank you very much. Any comments, questions?
If not, I have a comment, Thiago.
Okay.
This situation that you have explained at the end, that the existence of this limit cycle, it appears in a paper that you have done with how to say, with experimental researchers. Then this is quite surprise, the existence of this limit cycle for them, or not?
Yeah, because when, in fact, this model, no? These equations are placed at these papers, okay? And these equations were obtained by these people, not by us. Huh? We done the piecewise move study, and they look at these equations, and they are modeling a real situation, okay, where the virus is controlled and never eliminated. So this limit cycle, in fact, appears in the real real world, okay, in the real model. Okay, is this? And another important thing is that the other situations where we haven't a limit cycle corresponds to situations where we have a single point, okay, a single attractive point. And of course, in a real situation, they are, and these points are placed at a plane, okay, in a plane. Of course, so in the real situation, what we found is a limit cycle, because in a real situation, we always considering a kind of regularization or hysteresis around this sigma sigma is within manifold, and which appears in fact at the attractive set which appears is the limit cycle and not the single point.
Okay, and any other question? If not, so let's thank Thiago de Carvalho for this very interesting course, and we shall return in half an hour for the last lecture of this summer course. So thank you very much.